So in this lecture, we're going to talk about central vertices in binary trees, and this comes from problem 38 of Jeff's notes about recursion. So what's a central vertex? You could think of it as a node in the tree that's in the middle. Essentially, there's no imbalances on any side of the tree. So the idea is we take a node V that's in the middle of the tree, and what do we mean by middle? Well, the definition is going to be if we delete V, then the remaining subtrees have at most n over 2 vertices each. So essentially there's no imbalances around V. So if we had some V in a tree, maybe this is the tree, when we delete V, well, we have one node here, one node here, one node here, and in total there's n equals 4 nodes, so n over 2 is going to be 2, and so V is a central vertex. On the other hand, if we had a tree that looked like this, with a bunch of nodes over here, then V is no longer a central vertex, because if we delete V, well, this subtree over here has too many nodes. Another example is shown here. So we have a giant tree with 34 vertices, and here is a central vertex. The reason for that is if we delete it, well, the right subtree has 12, the left subtree has 7 nodes, and the rest has 14. And all of these are smaller than 34 divided by 2, which is 17. Okay, so that's what a central vertex is. Now our goal is to find an algorithm that computes central vertices. In particular, we just need to find one. And in particular, this is going to be a tree, not just any graph. Okay, so the hint in the problem says we should first prove they exist. So why do central vertices exist? Well, we can think of this by starting at the root. So if we look at the root, and the root has some number of children, we always know the root has 0 vertices in its upper subtree. So when we delete it, this region doesn't matter. There's always 0 vertices in the upper or parent subtree. So if the root is not a central vertex, there must exist a child that has many nodes in its subtree. So let's say it's this one. And this one has greater than n over 2 nodes. Okay, so if that one has greater than n over 2 nodes, well, what does this mean? In particular, that means this entire subtree, no matter how complicated it is, this whole thing has very few nodes. Why is this? Well, there's a total of n nodes, So if n over 2 of them are over here, at least, then at most n over 2 could be over here. Okay, so we know that's true, and so we can now focus on this subtree. Now when we go into that subtree, we immediately notice this node right here, just like the root, its parent subtree has to be small. So before the parent subtree had 0, now the parent subtree has at most n over 2. So we're kind of seeing a notion of progress appear. Every time we go deeper and deeper in subtrees, this parent tree is growing. So eventually, we would hope the parent tree gets big enough to where every other tree is too small. So here's the idea. If we move onto the tree, parent subtree grows, and eventually the parent subtree is going to get too big. So eventually, exceeds n over 2 nodes. Why is this? Well, consider a leaf. All trees have leaves, and at a leaf, we have one node and then the literal rest of the tree. So if this is a leaf, the rest of the tree has n minus 1 nodes, and if we keep going down the tree one by one, eventually we hit a leaf. So here's an example of a node with a large parent subtree. Okay, so we know we can keep moving, and eventually the parent subtree gets too big. But what happens right before it gets too big? The idea is right before the parent subtree gets too big, it must be that everything else isn't too big. So if we have some v, and we have some children of v, and let's say v is not central. So because v is not central, we again know there's some subtree with greater than n over 2 nodes. And at this point, when we move here, the parent has more than n over 2. So we're assuming this one, which we'll call w, w has greater than n over 2 in its parent. So if w has that many, something's gone wrong. So in particular, what's the difference between w and v? So we know v has at most n over 2 up here. So we've added all of those above v, and we've added these, and we get n over 2. So this whole thing here is greater than n over 2. But by assumption, this is also greater than n over 2. So we somehow have greater than n over 2 plus n over 2 equals n nodes. So it can't happen. In other words, at the node v, where any next step makes the parent subtree greater than n over 2 nodes, such a v has to be central. Okay, so that's the idea. Now formally we can do this with induction. So as you saw, there's this notion of progress, which is the number of nodes in the parent subtree, And so we could just induct where the number of nodes in the child subtrees is continuously decreasing. So we could prove this formally by induction on child subtrees we consider. And the base case will be at a leaf. Okay? So let's save that for a second. And now, assuming this property is true, what's the algorithm look like? Well, the algorithm's pretty simple. Well, there's two different ways we can do it, depending on runtime efficiency. So what's the easiest way to do this? What's the easy algorithm? So we could literally compute for the entire graph, compute for every node in the graph or in the tree, the number of nodes in its subtree. So we could do that. And then once we've done that, all we have to do start at the root, just like in the proof, and enter children. With greater than n over 2 nodes, which there can only be one by definition, until no such children exist. In particular, our argument above implies this algorithm terminates. So it won't loop forever. Okay, so we just started a node. We pick the child with greater than n over 2 vertices, and then we move to this node. And then we repeat the process. Really, it's recursive. Otherwise, if there are no children with n over 2 nodes in its subtree, then we're done. So otherwise, if no w has greater than n over 2 nodes in its subtree, then we know v is central, so stop and return v. Okay, so that's what we do if we already have computed the number of nodes in each subtree. And the question is, how do we compute that? And we can also compute that recursively. So how do we compute the counts? Well, we can do the following process. So the count for any nodes v is really just the sum of each child, v to w, of the count of w, plus 1 for v itself. So pictorially, the number of nodes in a subtree that looks like this well, this is just 1 for v plus the counts of all the smallest trees. So we can compute this recursively. We can just ask the recursion fairy to compute the counts for all children of V. The recursion fairy can do that because these are smaller height subtrees. Here we're inducting on the height, or we could be inducting on the total number of nodes. They're equivalent here. And then once we have those, all we have to do to combine the solutions is add them up. And then add 1 to that. So if we do this, the overall running time, we're going to do a constant amount of work per node. And so this will be O of n in total. Similarly, the overall algorithm is going to be O of n because we're walking through the tree, and we're going to, at the worst case, hit every node. We actually will never hit every node, but in the worst case, that's what we would just upper bound that with. So this is actually pretty fast because it's linear time.